Okay, let me start by sharing the screen. All right. Good evening. I don't think anybody else has joined now, but yeah. Okay, so welcome to the seventh live session for this course, and so we are through with half of the 12-week course. So do you have any specific questions about last week, this week, like except the um? I mean, we'll obviously discuss all of that, but or anything in general about the course, about assignments, exam, anything before we start? Okay. If not, um, okay. So yeah, as always, the lecture is going to be it's being recorded and it's going to be uploaded to YouTube and the PPT, and we'll also have an R script to discuss today. So all of that is going to be uploaded to this Google Drive. And all right. So today, like week 7 is sort of a continuation of week 6, where we discuss different types of distributions. Specifically, now this week we are talking about distributions for continuous random variables, okay, which don't take discrete values. So remember in a few weeks ago we had talked about how there is no probability mass function, but rather you have a distribution function which is denoted by small fx, and that by itself doesn't mean anything. You also cannot find probability at a particular point, so point probabilities don't make sense. You either have to have probabilities for an interval. um yeah, it has to be some interval. It could be like less than x, greater than x, between two values, and if it is less than x, then it is also known as the CDF, or the cumulative distribution function. So we will be using this quite a lot. So there are three types of distributions that we would be talking about this week. So I think I'll just explain it along the way, but mostly what I'm talking about is that this is where your x is, and this is where fx lies, and let's say a distribution looks something like this. So if you're taking the value of probability, this should be denoted by small x. So probability of x equal to, let's say a, let's say this was a, and that's going to be 0. But you can have some probability of this interval. So obviously this value um, would lie somewhere between 0 and 1. This the value here, whatever the value of probability is. And obviously the total value of probability, which is this entire thing, okay, the entire space, that obviously the probability is going to be 1, because that's the total thing. So it's area under the curve that we are going to be interested in today. So the total area under the curve is going to be 1. All right. So the first thing is continuous uniform distribution. So again, from last week, this is the kind of notation we are using. So x is a random variable which has a distribution u denoting uniform. And there are two parameters. There are just two things that you need to know. That's a and b. By convention, a is the smaller value, but as such, the direction here does not matter so much. And so even if you take it the other way, if it's left to right or right to left, it doesn't matter. So again, so this is what it's going to look like. On your x-axis, you have a somewhere, you have b somewhere else, and this is again the fx function. So the distribution is, as long as x lies between a and b, so it would have a constant value, and that constant value actually is 1 upon b by a, 1 upon b minus a. And why this is so, we'll just see in a minute. And everything else, the value is 0. So as soon as you go before A, the value is 0. And as soon as you go after B, the value is again 0. Again, so the length, again, so this is a rectangle, right? Area of a rectangle is length into breadth. Now, and the total area has to be 1. So the length here is B minus A, this length, and width, let's say we are calling it, let's say this was W. This is W, that's 1. So obviously W comes out to be 1 upon B minus A, and that's this value right here. So again, this is not something you have to remember. So because like remembering 1 upon B minus A, what if you make a mistake somewhere? So it's easier to just derive this thing. Expectation, again, this is very intuitive because it's a constant value. So obviously the average or the mean is going to lie in the center. So that's going to be A plus B by 2. So that's the center value. Variance, yeah, that's B minus A whole square by 12. That's that. We're not really deriving it, so that can be remembered. But yeah, so that's continuous, that's the uniform distribution. One thing which we'll also see a little bit later in one of the, actually we'll come to it while we are solving some questions. I'll talk to you about at that time. Uh, Inverse transformation, this was just something extra that was discussed in the lecture. I'm not sure if you would get any questions about this in any of the assignments. Oh, I can see some more people have joined us. Welcome. So yeah, so again, this was just the basic first slide that we just saw. So we're talking about continuous random variables here. So area under the graph is what you're interested in. And for a uniform distribution, it makes a rectangle, so calculations become easy. The important thing to remember is what is this y-axis value, and that is something that you can calculate when you consider area is equal to 1. Inverse transformation, this is just to sort of know how. So remember last week we had these functions which are like R binom, which we were using to generate random variables, right? Or R poise for Poisson distribution and so on. So this is how it's doing it. It's it's basically doing an inverse transformation, that what values would satisfy a given criteria. This is just more for your information. Again, right? If you have to uh, suppose this is how it is, the function is that x to the power n gives you some value u, then the value of x is going to be u to the power 1 over n. But again, this is not something you have to worry. Sorry, was there somebody saying something? No. Okay. Yeah. All right. So that's that. Now comes the major bit that was covered this week. So normal distribution, and please let me know if at any point of time you're confused. Um, the understanding this would help you tremendously solve most of the questions that are there for the assignment this week. And also, like, just this is definitely something useful to learn. Okay, so this is the general formula of a normal distribution. So 1 upon sigma and within root 2 pi, and the exponent basically, which means e to the power this value. Okay, so that's negative of x minus mu whole square upon 2 sigma square, where mu, as we often denote, is the expectation or the average, and sigma square is the variance. So obviously sigma is the standard deviation. Okay. All right. Now, so we'll talk about this maybe over the next 15-20 minutes, I guess. So again, what you're going to be looking at is some sort of CDF, right? Less than a certain value, more than a certain value. And so let's just draw it out. All right, so For example, this is what a normal distribution looks like, okay? And obviously, this is where mu is. Now, again, obviously, we're looking at probability, so we're looking at area under the curve. Every time we're looking at areas, we will be referring to areas in terms of the CDF. For example, obviously, this is the conventional CDF, everything less than value. Okay, so that's directly the CDF. If you are interested in, let's say, a value which is greater than something, then you will say 1 minus whatever is not shaded in red. So that's also a sort of CDF. Third example, when maybe, let's say, oops, I'll take this color. Let's say next example, maybe when you're looking at a chunk here. Okay, so then you would be taking this CDF and then you'll subtract this CDF. So you get the center area, right? So this is something we've also discussed earlier. So I'm sure you're aware of this. In case not, please let me know. Please don't worry about asking questions. I mean, please ask questions if this is not clear. So everything we're doing is in terms of CDF. Okay. Now there are a lot of ways in which you can calculate the CDF. Obviously, um, there are tables available online, and these would be provided to you in exam if some sort of calculations have to be done. We can discuss the tables maybe sometime later. I don't have the tables with me right now. But what we'll do in today's session is we'll solve it in two ways. We'll use R, and we'll also use these online um, these there are some web pages which we'll take a look at and solve this, and these really help you get an idea of what you're dealing with. Okay, but before we go there, so this is the general way of normal distribution. So X random variable is normally distributed with mu and mu as the mean and sigma square as the variance, or sigma as the standard deviation. Yes, so this is just something you should keep in mind because it's very easy to. Oops, what happened? Sorry, my pen stopped working. Just give me a second. Did I press something in here? Oops. What happened? This is working. Sorry about it. Just give me 1 second so I figure out what's wrong. Never mind. Let's see how it goes. Okay. So another way to do is if instead, what happens if instead you use a different, so this is one case. Another case is what if the value of mu was actually 0 and the value of sigma was 1. Okay. If so, that is like a special example. So where so that sort of an example is referred to as the standard normal distribution, and it looks a little bit simpler because now here sigma you replace it with 1. Here this is 0, so it directly becomes x square, and here again that's 1, so it just becomes x square minus x square by 2. Okay, so that's relatively simple and it looks good. All right, so that's all okay. What you can actually do is you can convert. So the original random variable was x. What you can do is if you subtract mu from it. So let's say there's a random, all of these values of x. Okay. If you replace x with x minus mu upon sigma. if you subtract mu from all of your random variables, and if you divide all of them by sigma, then you get a new set of random variables. We'll call that Z. And that Z is going to follow a standard normal distribution. So remember, you have, let's say you have 100 variables with you, 100 random variables. You're calling them X. You're just transforming them. You're just subtracting a particular value from all of them and you're dividing all of them by another value. So there was one set of random variables. Now you have another set of random variables. The original set of random variables uh, gave you a normal distribution. The new set of random variables will give you a standard normal distribution. That is all. Uh, all right. So we'll see how this is put to use. Okay. Now, if you can get two different plots like this, and then you can say that if there is one random variable which has, let's say, sigma square as 2 and another has sigma square as 10. So what you'll see, variance, the more the variance, the more spread out the graph would be. Okay. So now I'm sorry, my pen doesn't work. So I'll have to draw it using the mouse pad and it's again not going to look good. But so for example, if this is a distribution and if this is a distribution, okay. Here we are not exactly interested in what the peak is like, but obviously the area under both the curves has to be 1. So what you are comparing basically in this plot is that this one, if this one has sigma 2, and if this one basically, let's call it sigma 1, then you can say that sigma 2 is greater than sigma 1. Okay. And different values of mu, then it's just going to get shifted left or right. Okay. Again, for example, if this can be mu1 wherever the peak is, and this is going to be mu2. Another thing, I don't think it's explicitly mentioned in the slides, but the mean median mode of a normal distribution is all at the same point. Okay, so that's that. So yeah, mean and variance, since those are the parameters that you are providing, so you can't really comment on that if sigma is high, what would be mu like? If mu is this, what would be sigma like? You can't compare one with the other. They are both independent properties. Okay. Um, and if you have a random variable which you are saying that it's something times a random variable plus a constant, where x is a normally distributed random variable, then you can say that the expectation of y, it's just going to be on those lines. It's just simply replacing x with y. But the variance, well, that extra constant that you're adding, it's just shifting the graph left and right. So that's not going to affect the variance. But this extra constant that you have multiplied to your variable, that would change your variance. So that variance, you're dealing with squares of numbers, right? So it was ax. So now it's a sigma, but it's variance. So it's a square sigma square. That's that. Now, so if you remember, okay, so this is a symmetric graph, right? So a lot of things can be interpreted quite well. And this is not just because it's symmetric, but also because it follows a pattern. So what you can see here in this graph is there's a central value mu, and you can obviously now on the left, you have values lesser than mu. On the right, you'll have values greater than mu. You can take some specific values on the x-axis. Now, these are mu minus sigma, mu plus sigma, mu minus 2 sigma, mu plus 2 sigma, mu minus 3 sigma, and mu plus 3 sigma. If you take these values have sort of been, I should say, these values have been calculated that the probability or the shaded areas that you can see here, you actually have the probabilities with you. So the dark green shaded area, which lies between mu minus sigma to mu plus sigma, that is 68% of the total area. Obviously, you can calculate from there that, okay, the half of it is going to be 34%, 34%. Likewise, the area between mu minus 2 sigma to mu plus 2 sigma, that's 95%. And the area between mu minus 3 sigma and mu plus 3 sigma, so total of basically 6 sigma centered around the mean, that is going to have 99.7. So in probability terms, it amounts to 0.68, 0.95, and 0.997. Are we good till here?
Yes, ma'am.
All right, okay. Another thing for, yes, all right, thanks. My pen is still not working. What's wrong with it? Never mind. Okay, so for example, you can think of a case where, let's say, if the question is that mu is 20, let's say sigma is 3, or very often you'll actually be told sigma square, right? So from sigma square, you'll have to actually calculate sigma. But okay, when you've calculated that, let's say you are asked, what is the probability that x lies between, let's say, 23 and 17? Okay. If this is a question, then you can actually see that, okay, you are asking something to be at a difference of 2 sigma, right? So it looks like this sort of a difference. And obviously, the center of these two values, it's not just, so, okay. Another thing, if the question would have been, let's say, okay, suppose these are two questions that you're asked. Now, in both of them, the difference between the minimum and maximum values that you are being asked, the shaded region, both of them is at a span of 2 sigma, right? But only one of them is mu minus sigma and mu plus sigma, which is this one, right? So for this, you can use this sort of axiom, and you can say that, okay, this value is going to be 0.68. You don't need to calculate. But for the second one, you can't do that, because basically then maybe what you're trying to calculate is this area. And we don't necessarily know about this area, right? Because now it would probably be lesser than the center. The center is the most, the biggest area, right? Does this make sense? Yeah. Okay. All right. Okay. Now, before we go into this, I will just open up that page here. Oops. Mm, okay. So now what you can see here, so it asks you to give some value of mu, some value of sigma, and some value of x. And then you can calculate probabilities that do you want area more than that x? Do you want the area which is less than that x? Something about the modulus also, so the two extremes, or something in between. So I'll just show you what this is. And then the thing is mainly that with this sort of an application, it just becomes more clear about what you're dealing with. Okay. Maybe this is already clear to you, so this might seem redundant, but it's still worth spending 2-3 minutes on this. Okay. So first of all, if I'm just, so right now you can see that the plot here, it is centered around 0, because we have set 0 as the mean. That's the default. And the variance here is 1. It may not seem apparent, but the variance is 1. The maximum right now here is at something around 0.4. If I just change the variance to 2, and so you can see now the graph doesn't look different, but now the values here are different. So now the peak has reduced and it's actually flattened. So the peak is now shorter, and the left and right sides have broadened. Okay. If I change the value of mu, Again, graph looks the same, but now the center value is different. Okay, so with that, you can change it to a normal distribution or a standard normal distribution. That's that. And then maybe now questions would be, let's say something like less than a certain value, more than a certain value. So when you're dealing with, let's say, less than, maybe everything that is less than, so one would lie somewhere here. Maybe I can write one here. And then it just shows you that, okay, that's where you've selected, that's where your one lies. And since you have selected probability of everything less than this one, so that's the shaded area and that's the thing. You can select greater than, it would be the larger area. Of course, you can do it the other way around with one minus thing can also be calculated, right? So, I mean, you have this. If you want to calculate the larger area, you can do 1 minus this value. You get the larger area. Yeah. So, you remember we just talked about minus sigma to, mu minus sigma to mu plus sigma. So, let's say if the region here that's from, maybe I'll call it 3. So, what we are looking at is region between 1 and 7, right? So if I say 1, I get this value. So I get 0.15 roughly. And when I'm saying 7, I get 0.84. Now 0.84 minus 0.15, that's roughly 68, 69%, right? So that was the center area we just talked about. I hope I'm not confusing you. Okay, so the thing is that with this sort of a setup, you can calculate. So obviously a lot of manual work still has to be done, but then these shaded areas values you can calculate. And if you remember when this was 0 and 1, when we were talking about the the standard normal, you got a few more options here. So that's just because it's a standard normal variable, standard normal distribution. But again, it can still be done manually when you don't have a standard normal. But now let's talk about converting a normal to a standard normal. Um, yeah, so I think this we sort of just saw that. So here, okay. So let me. Uh, pen is still not working, right? I don't know what's wrong with this. Oh, buttons pressed. All right. Can't help it. Let's see. I've not got a notification, right? That this is not working. Okay, fine. So now what I can do is, let's say we're again drawing um, this thing here. So suppose you've selected a value A, okay? Maybe let's call this, so for all practical purposes right now, we'll just assume that this is 0. And if you've selected a value here A, then this is symmetric, so it's going to be minus A here, okay? So if you're looking at everything which is less than minus A, which is basically this region. So very often, again, more use of this is going to come in future classes. But a lot of times, shaded areas towards the ends are often referred to as alpha. Okay. This has something to do with tests of significance and p-values. Just mentioning it right now, but we're not talking about it at the moment. Okay, so very often these are referred as alphas. So the point of x at which you are making that cut, that's A, but the shaded region is called alpha. Okay. Likewise, since it is symmetric, so this shaded region is also going to be alpha. Okay, that's that. And if you are looking at this entire shaded region, okay, everything from here to here, okay, then obviously you're subtracting the yellow region from here. Okay, that's that. If you're saying z less than minus alpha, so it's this portion, the red one. So it's this and this, right? So it's 1 minus alpha plus alpha. And you can also see that since you're talking about symmetric areas, all of this adds up to 1, right? Because you're covering the entire thing. And obviously, symmetric, so less than 0 is 0.5, more than 0 is 0.5. So um, this is something on the lines of one-tailed, because you're looking at one end at a time, okay? You're either considering less than, you're considering more than, left half, right half, you're just considering one part at a time. Now, when you're talking about two-tailed tests, okay, again, what we are plotting here, it looks the same, okay? Again, this is centered around 0. Here you have minus a. Here you have plus a. But now, what happens is you are interested in both of these areas together. Again, so by definition, again, the definition of that we'll cover a little bit later. By definition, this area, like, let's call it, I'm just calling it A1 as area 1. And if this is area 2, then what we're doing is A1 plus A2, we are calling that as alpha here. So obviously this means that this is going to be alpha by 2, and this is also equal to alpha by 2. Because the total thing you want alpha. Why? Again, uh, I'm not explaining it right now. But the thing is, at any point of time, when you're looking at the left end, also you are interested in the total area to be alpha. When you're looking at the right end, you're looking at a total area to be alpha. When you're looking at both the ends, then the total area should still be called alpha. It's just what you're calling as alpha. So obviously in this case, these are smaller chunks because the total thing is adding up to alpha. Here, just one side was adding up to alpha. Okay. So again, clarifying. So basically, this side is probably when you're looking at two-tailed tests, and this whole thing is probably when you're looking at one-tailed tests. Again, we'll talk about it later, but shaded area at any point of time is generally referred to as alpha, totally. But this can change according to definitions. But when you're looking at one end, you're calling it one-tailed. When you're looking at both ends together, you're calling it two-tailed. So basically here, you're looking at the center area. So you've subtracted alpha by 2, so you've subtracted alpha in all. So you're calling it 1 minus alpha. Okay, that's that. Let me know if there's any confusion here, but don't worry about this too much. I just wanted to let you know so that when later we discuss it becomes clearer. So now what we are doing here is we are transforming the random variable. So again, let's say this is what the question was. Find the probability that x is less than a, some value of a. Okay, so again, forget about that alpha and a for now because we're not talking about that. Suppose this is a, and this was basically mu, and the value of sigma here was sigma, right? That was the variance. So this is the question. Now, it's often difficult to, I mean, of course, you can calculate anything, but very often if you're using these manual printed tables, if time permits, I'll show it to you today in the end of the class, or we'll discuss it next week. But yeah, you can just Google it, normal distribution, standard normal distribution tables. So what happens in that, since you already know, so you don't have multiple parameters. Mu is already 0, sigma is already 1. So there's no confusion. There's just simple values. Okay, there's one value that you have to find in that table. So it's sort of given. With mu and sigma, there could be countless combinations of mu and sigma. So everything is converted to 0 and 1. So again, this is simple sort of simple algebra. So, okay, it's an equation. So both the left and right side of the equation, you subtract mu and you divide by sigma. The left side, now you're just calling z. So if earlier, let's say the question was that what is the value, what is the probability that x is less than 3? Suppose this was the question. And if mu, let's say, was 5 and sigma, let's say, was 2. Sigma square, let's say it was 4. So sigma was 2. So now the new thing becomes that z is equal to 3 minus sigma is 5. And this, sorry, mu is 5, sigma is 2. So now this is minus 1. Right? So now you just have to find that now you have a standard normal distribution centered around 0. Minus 1 is going to be somewhere here. So you just need to find the area that's here. And then we already know how to do that. This was that. You just simply write minus 1. You get this value and you're done. Same thing. Let's say if the original question was sigma is 5. Oh, sorry, mu is 5. Sigma is 2. X was 3. Now you see you still got the same value. 0.15866. And right, if I did this, I still got 0.15866. Right? So both of them, you get the same value. It's just choosing appropriate value of x given what is your combination of mu and sigma. Does this make sense? Are you able to follow?
Yes, ma'am.
All right, great. So that's for when you are talking about less than a sort of notations. If it was greater than a, then obviously, yes, okay. If it was greater than a, you can simply convert it to 1 minus sort of a setup and it looks the same again, right? If it is a central value, so something between a and b, then you convert both of them. You do this, and then basically you know that it is two CDFs that you have to subtract. The larger area minus the smaller area. Okay. So again, these are more a lot of variables here, but it's really doable. Okay, we will solve a few examples today. So it's a relatively longer lecture. Okay. Yeah, so I think this was also mentioned somewhere. So if you have lot of normal distributions, okay, each of them is a normal distribution. So if you're taking averages, so the average of all of them, so each of these are normal distribution. The average of normal distributions will also follow a normal distribution, with the mu being the same, but the variance gets divided by n. Okay. Uh, so yeah, I don't think there was any proof or any questions for this. Yeah, these are more sort of extra information. I'm not 100% sure how these would be asked in questions, but a few of these things I think you would have to remember. That I don't think there's a great solution to that. But yeah, that's that. Um, okay. Now we talked about binomial distribution and Poisson distribution last time, right? And these are both for discrete variables. But you can approximate both of them to a normal distribution. Okay. So if you remember last time, if you take a look at what they looked like, what sort of a graph, they do have this sort of a graph somewhere. Okay. It's not perfect, but there are certain conditions where these two work. So for a binomial distribution, you remember the parameters were n and p. Okay. K was obviously user specified. So n and p were the parameters that explain. Okay, so it was binomial n comma p, right? So based on if multiplying np is greater than 5, and np multiplied by 1 minus p is also greater than 5, then um, you can use you can approximate a binomial distribution to a normal distribution. And the thing is, it becomes simpler to calculate values. Okay, so this was the thing. This is something we remember, right? So both expectation and variance, if both of them are greater than 5, um, then we can approximate binomial to normal. And what we would do is, so what you're doing here is that random variable, the binomially distributed random variable, you subtract the mean and you're dividing it by um the standard deviation, right? So the root of the variance. So that's the same thing. Okay, you're getting the standard normal. The only thing is, you're converting a discrete value to a continuous value. So there is a continuity correction that needs to be done, where you're just adding zero point 0.5 so that you are taking into account the discrete and to continuousness. Again, I am not 100% sure of why this helps, why this works, but that is how it is. So so here you'll just add that value. Okay. So that's that. Again, we'll see some examples, we'll solve some questions. And the same funda applies to a Poisson distribution. Again, here you only just have lambda, right? Both mean and variance, they're both equal to lambda. So here also what you're doing is x minus expectation or mean divided by root of lambda, which is standard deviation, right? And here too, you will just add 0.5 to whatever is being asked. Okay. All right. So we've talked about normal distribution. We started off with uniform distribution. We have talked how you can approximate Poisson and binomial to normal distribution. The final thing is exponential distribution. Okay. Again, the way you're referring it to as is E or EXP, and in brackets you write lambda. So remember, exponential distribution, like Poisson distribution, says something like lambda, but both of them behave differently. There are different formulas. The expectation and variance also follow different patterns, and the PDF, CDF, all of them follow different formulas. So don't get confused. Okay. So remember, for geometric distribution, um, the case was that where is the first success coming? So here, exponential distribution is also for that. Where is the first success coming? But it's for continuous random variables. So again, only positive side of the quadrant between 0 and infinity. That's lambda e to the power minus lambda x. And the CDF here is going to be 1 minus uh, e to the power minus lambda x. That's the CDF. The expectation and variance, that's 1 by lambda and 1 by lambda square respectively. Like geometric distribution, and I think also Poisson distribution, this has lack of memory. So it doesn't matter if you're looking at between 0 and 10 and 10 and 20. The trend stays the same. Something so this thing is sort of a clue for one of the questions we'll discuss right now, like maybe in another 20 minutes or so, in a little time. So it's always good to check what units you're looking at. Typically in probability, very often, since you're not dealing with units, you're not very worried about it. But uh, well, the questions that you'll be dealing with, they could be something around kg, distance. So maybe like weight, distance, time, right? These three things. More often than not, it's one of these three things. So now the expectation. So suppose X here, suppose X is in kgs. If it's given in kilograms, what would be the unit of expectation? Expectation of X, what would that value be? Anybody?
kg, madam.
Sorry, say that again.
Kilogram.
Yes. So expectation would also be kilogram, right? Now, if expectation is kilogram, then what would 1 by lambda be? So 1 by lambda is kilogram. So that means lambda has a unit of kg inverse. 1 by kg, right? But the thing is, if this is kg, this is also kg. Just keep it in mind and we'll see it in one of the questions. Okay, before we go to the questions, we'll have a quick demo of some of these distributions in R. Again, this is very similar to what we talked about last time, the four distributions, D, which is talking about the PMF, or in this example, the PDF. Um, then you have the P, the name of the distribution, which is for the CDF. Then you have Q, which is telling about the quantile, and then R, which is for the random number generator. So since we have a lot of questions actually to solve today, I will go through it, but quickly. And again, this is very, very similar to what we talked about last time. So I don't think it would be a problem, but let's see. So again, for uniform distribution, uh, you have to specify a minimum and maximum. So basically A and B, right? But just to avoid any confusion, these are called min and max. And then which of these values? So X here, it's basically what values of X you want. So the thing is, A is 0, B is 20, and okay, maybe I can call this minus 10 actually, because it doesn't matter where I'm going from. So it's this. So you can see the initial few values are 0, right? It's so the output here, all of these, let me increase the font. So the output here, these are basically the y-axis. This is going to be our x-axis, and this is y-axis, the output. So you remember this, this thing that we just talked about. So up to us at a certain point, which is lying between a and b, you'll have some value, which is going to be 1 upon b minus a, and everything before and after that is going to be 0. So that's what you can see here also. So everything between 0 and 20, that value is 1 upon 20 minus 0. So it's 0.05. And everything before that is 0. Everything after that is 0. So you can plot this simple XY plot. Let me call this actually minus 10, minus 10. Yeah, this thing. Okay. This is what it looks like. Okay. Another, yeah. Okay. So yeah, another thing, I don't think this function we talked about last time, but curve function is can be used with these uniform, with any sort of distribution functions. And you don't have to specify ranges. It will automatically select ranges based on what it can do. Okay. For example, here I'm just calling it X. I'm not giving it any value. Like here I gave it these values, minus 10, minus 9, so on and so forth until 28, 29, 30. Now I'm not giving it any values. I'm just saying plot it on your own. It plots it, not very explanatory. So I can specify X limit. Again, this is just extra information just so that you know what's happening. So here it looks better, right? Now it's more understandable that okay, everything before 0 is 0, everything after 20 is also 0, and everything between that is 0.05. Then P, that's going to be used for probabilities or CDF. So again, the value up to which the probability is to be calculated, because remember by default, lower tail was true. So if we are doing it value up until 5, so you can see this is 1/4 of the total value. So you should get 0.25, and that's what you get. If you want to find values great, like what is the probability of x being greater than 5, you can either do 1 minus the first thing, or you can do a lower tail false. That gives you 0.75, so that's also okay. Quantile, if you want to find at what value of x does the probability up to that value fall to be 0.6, then that's going to be somewhere here. So this total area, that's going to be 0.6. So that also holds true. Again, you can also do a lower tail false here. So it's going to be reverse. So 8 and above, everything is 0.6. RUnif, that's going to be used for random number generator. Again, the first value is going to be how many numbers you want, and the next two values are min and max. So if you want 10 values, it's going to be that. As many times you run the random number generator, you're going to get different set of values. Okay, never are you going to get the same set of values again. All right. Okay. And of course, this is again the same thing. If you have normally, the more values you take, the better approximation for mean and variance you'll get. So here, when you took 10 values, you got 13 as the mean. When you took 100 values, you got 10 point something as the mean, and 10 is actually the mean, so it's closer that way. Variance, again, 33.33 is the variance. You remember the formula for variance was b minus a whole square divided by 12. So that comes out to be 33.33. Ideally, neither of these values are great, but yeah, the one with 100 is a slightly better approximation. Okay, cool. So that was uniform distribution. Then we have the same 4 formulas for normal distribution, starting with d-norm. So if you're talking about a standard normal distribution where mean is 0 and standard deviation. So yeah, so remember here, when we are talking about normal distribution, you are generally denoting it by mu and sigma square. So if I say n in brackets, I write 2 comma 5, then 2 is mu, but 5 is sigma square. So sigma is actually root 5. Okay. But in R, what you have to specify is SD or standard deviation. So had it been for that question, you will have to specify root SQRT5 as the standard deviation here. Okay. So again, if you want to find values like this, so you can see here, the smaller the value, it was really small, then it kept on increasing up till somewhere, maybe somewhere here is where you've got the maximum value, and then it keeps on decreasing again. So of course you can also plot this directly. So plot minus 10 to 10, and then this thing. So this is what it looks like, right? Maybe plotting it between -5 and 5 would have done a better job. Sorry. Something like that. Yeah, maybe it looks slightly better. But yeah, anyway, so this is what a standard normal distribution looks like. We can also use the curve function directly. So yeah, so the curve function here, it doesn't do a good job. It directly just plots on the positive axis, but we know a normal distribution is distributed along both positive negative axis. So we can solve this, we can explicitly specify the X limits. That's that. You can go further. This does a better job, right? It looks like an actual normal distribution. And of course, you can take more cases, different values of mean, different values of um, standard deviations. So you see here, the standard deviation here, this was 3, mean was 20. So it looks really like a thin graph. At 10 and 30, it has already tapered. But when I'm increasing the standard deviation to 5, it looks broader now. Okay. Yeah. Anyway, so that's the d-norm function. Then the p-norm function is going to give you um, up to values, right? The CDF. So probability of getting up to 18. So it's the 20 and standard deviation 2 example. So yeah, when you're saying 18, it would be somewhere here. So it should cover less than half of your value. Oh, the standard deviations 2. So wait. Let me just plot that out. Maybe I'll say 10 and 30. Okay. All right. Yeah. So this is what we are plotting. Okay. For this question. So when you're saying 18 and below, so it's just covering the small area. Okay. So then you get 0.158 or 15.8%. So that checks out, right? It's a really small area. So drawing out very often helps you, not so, again, for normal distribution, it's not always possible to draw it out. But if you're able to plot this, for example, in R or in that web application, then it does help. Likewise, if the mean is 0, standard deviation 1, so it's a standard normal, and you're saying you want to, I think this was one of the questions. So this is actually converting this thing. So yeah, if you convert this um, normally distributed variable to a standard normal, so that's going to be x minus, so it's 18 minus 20 divided by 2. So 18 minus 20 is minus 2, minus 2 divided by 2 is minus 1. So it gives you the same value. Okay. So again, this is another way. So you can either do it on the web application, you can also do it on R. It checks out. I don't think I have these written as such for the quantile and yeah, R norm. Again, the story still follows. Okay. Just like before, you have these things, you specify n, you specify mean and standard deviation. So yeah, if the mean is 0, then you see here, when you're taking 10 observations versus when you're taking 1,000 observations, the mean is 0. You're specifying mean is 0, but the mean you get is 0.6. But when you're specifying 1,000, you get mean which is quite close to 0. And same way, when you're saying standard deviation is 1 or the variance is 1, so you're getting 0.9 and versus you're getting 1.03. So obviously this is a better estimate. So the story continues. We go to exponential distribution. Here it doesn't call it lambda, but it calls it rate for the exponential distribution. So again, we specify the value of x. Again, as a vector, you can specify. But yeah, so this is what it's going to look like. So remember these exponential distribution, they start off at 0 and then they taper down. So if, yeah, so anything, so x limit less than 0, it's just telling you that it's going to be 0, right? So that's that. Again, CDF, quantile, random distribution generator. Yeah, for lambda, if you say lambda is 2 or rate is 2, then mean is 1 by lambda, so that's 0.5. Variance is 1 by lambda square, so that's 0.25. Again, when you do 10 versus when you do 1,000 gives you a better estimate. For variance also, 1,000 gives you a better estimate. So the story is all the same. Okay. Are we clear up till here? Do you have any questions till this point? Okay. If not, then we can go ahead and solve some questions. Now, there's a lot of questions, I think. Okay. Let's go. Alrighty. So again, please, yes. Okay. So yes, please let me know. So I mean, not just let me know, but yeah, please solve these questions alongside. It's okay. You don't have to give me exact answers, but you can just we can just sort of go around and just discuss how to solve it, and then I'll give you the answer so that you can also solve it later, because I do have these questions solved with me, so I don't mess up. Hopefully I don't mess up this time. Okay, so, and apologies again, my pen doesn't work still, so I'll have to write it, so please bear with the speed and the handwriting. Okay. So suppose a train arrives at a subway station regularly every 15 minutes. If a passenger arrives at a station without knowing the timetable, then the waiting time to catch the train it's uniformly distributed, right? So it's like this. Suppose this is 0 and this is 15. It's going to look something like that. Right? Okay, let's call this 15. And obviously this is going to be 1 upon b minus a. So 1 upon 15 here. That's what's given to you, and 0 otherwise. So nothing here, nothing here. What is the probability of waiting for up to 5 minutes, waiting for 5 minutes, and waiting for at least 5 minutes? Now, you have multiple ways of solving this. You can obviously plug in these values in R. Okay, you have the unif functions, the p unif function, right? So, which we just saw here. These ones. You can specify this 5 thing here. You can specify 0 and 15 min and max, and you'll get those values, right? You can also integrate. Okay, you remember 1 by 15 integration dx, something like this. So 1 by 15 dx, and you can integrate this from whatever to whatever. 1 by 15 comes out, integration of dx is just x, so it becomes x by 15, and you plug in the values. Or simplest, you don't need to solve any formula based or command based thing. You can just look at it. Okay, 5 is going to be somewhere here. So what do you think the answer for the questions are? We don't have to solve them. I mean, we don't have to solve using the calculation, but we can already get the answers. What do you think is? Okay, first of all, what is the probability for waiting for up to 5 minutes? What area should I shade here? What area are we looking at? Come on, this is simple. One of you can just unmute yourself and say, don't be shy. And it's okay if it's wrong. There's absolutely no problem. No, nobody.
Excuse me. Ma'am, which question you have asked?
So, so for this question, for question 1, what is the probability of waiting for up to 5 minutes? What area are we going to shade for that?
Area which is less than 5, that is between 0 to 5.
That is between 0 to 5. So it's going to be this region. Right? So it's going to be this chunk that we are shading. And just from the looks of it, what do you think the area is? So
it must be 1/3. Total area is 1.
yes, perfect.
And 0 to 5 is almost 1/3 of that.
It has to be exactly 1/3 of that. But yeah, yes, you're on the correct lines. Because if you can, like, you can see it from the area of this rectangle also. The width is 5, or like the length is 5 and the width is 1 by 15. So 1 by 15 into 5, so that's 1 by 3. The second question is, what is the probability of waiting for 5 minutes? What area are we going to shade here?
Exact probability should be 0 or exactly 5 minutes.
Correct. All right, great. And then for the last question, which is waiting for at least 5 minutes. So that's going to be the rest of it.
Complement of first one.
Yes. So that we get as 2 by 3. Okay. Again, if you do solve this question using like the integration, which we have done previously. So let's say for question A, if you wanted to solve between 0 and 5. Okay. So 1 by 15 comes out. It's integration dx, that gives you x. So that's from 0 to 5. So again, that's 5 minus 0 by 15. So it's still by 5 by 15. And it's again 1 by 3. So that also gives you the same answer. And just for the sake of this question, I will also just show it on R, just so that we know we are doing it right. So the function is punif. So the value of 5 that we're looking at, the value of q that we're looking at is 5. Minimum for this is 0. Max for this is 15. And lower tail is true by default. So you already get 0.333, right? And obviously we can do a 1 minus this thing for the third question. So that's 0.67, right? Okay, so we are working it. Yeah. All right, cool. Then the next question is that an apple farmer sells apples in boxes. The weights of these boxes vary and they are assumed to be normally distributed with mu as 20 kgs and sigma square as 4 kgs. So a very good practice here is going to be to calculate sigma, because a lot of places are not going to use sigma square. You will use sigma. Look what I've written. So sigma is 2. Okay. Now there are 4 questions which are all very related. So a farmer wants to avoid customers being unsatisfied because the boxes are too low in weight. So what's the probability that the boxes weigh less than 18 kgs? The farmer also wants to avoid losses, that the boxes are heavier. So they want to know what's the probability that a box would weigh more than 22 kgs. Find the probability that the box weighs between 19 and 21 kgs. And what's the probability that the box weighs more than 25 kgs? So like the previous question, we can manually solve this. Okay. Like we can do a lot of calculations. We can directly put in on R. Okay. We can do it on these website also, right? We can either go with the actual values or we can convert it to a standard normal distribution. So for one of these, I'll solve, but for the other 3, I'll just give you what the answer is, but I will not solve them because it's going to take a lot of time and then we might miss out on the other questions, because what time is it? Anyway, okay. So it's, yeah, we already completed half the time. Okay. So, and also I won't solve everything because it's going to take up a lot of time because I'm manually writing all of this using the trackpad. Okay. Anyway, so let me solve question B here. Okay. So the question is that the probability x greater than 22. Okay. Now what we can do is probability, wait. So what we can do is we can write it as, generally it's always less than equal to sort of a case. So we'll write probability X less than, here these greater than or greater than equal, less than equal, these don't matter. So don't get too worried about that. Okay. So this is the, yeah, so this is the thing. Now, if I want to convert it into a standard normal, what I'll do is I'll say Z, and then instead of 22, I will have 22 minus 20 upon 2, right? So that's 1 minus the probability of, sorry about that. Okay. So 1 minus the probability of Z being less than equal to, so that's 2 by 2, that's 1. Okay. Yep. So that's it, right? Now, if you want to calculate this value, let me actually show you the normal distribution table here. Normal distribution, standard normal distribution table. Okay. Not this. Yeah. Mm, Okay. All right. So, for example, so let's first solve this and then we'll check if we are able to find this in the table also. Okay. So what we want to do is, so let's do it a few different ways. Maybe it'll take a few minutes, but just for the sake of it. So a standard normal distribution. So that's like 0 and 1, and we want to find 1 minus p z less than 1, or in totally z greater than 1. So here we have our normal distribution thing, the standard normal, and this is 1. And we mainly want to find greater than this, right? So it's that value. We just saw this value earlier, but yeah. So it's 0.15866. Had we used the actual thing where the mu was 20 and the sigma was 2, and then we wanted it to be 22, then we also get the same thing. So it's again, it's just a coincidence we have taken same values again, but it's giving us 15866. Okay, now we go to this table and the value we wanted was 1. Uh, this should be greater, right? Mm. Hmm. Interesting. This is why is this 3, 4. I think this is like a two-sided thing. I don't know. Okay, wait. I don't want to confuse you with this. To the left of Z score. Yeah, so it's like that. So we're talking about 1, right? Yeah, so it's this value. Okay. So again, remember what this plot is telling you is actually this thing. And then you want to calculate the right half, so you do 1 minus this value. Now it's 0.84 here. And so if a Z value, if you want 1, then that's 0.84 again. So, the way you have to read this table is, if you want the value to be 1, it's this. If you want the value at 1.1, it's this. If you want the value at 1.01, then it's this value. 1.02 is this value. 1.05 is this value, so on and so forth. 1.09, 1.1, 1.11, 1.12, so on, 1.2, and so on. Does this make sense? Yeah.
Yes, ma'am.
Yeah. So this sort of a table is maybe what you might get in your exam. Again, so this is just for a standard normal. You're not bothered about what's the value of mu, what's the value of sigma. So these tables only work if you have standard normals, right? So which is why converting x to z, converting a normal distribution to a standard normal is good. But when you're using a app like this, it doesn't matter whether you're using a normal distribution or a standard normal, because you can set mu and sigma here. Likewise, you can also solve this using R, okay? Because you have the P norm function, okay? Again, let's say we want to find it at 1, and the mean is 0, standard deviation is 1, you get that 0.84 value, and obviously you can do a 1 minus this thing. You could have also done it, the 22, 20, and 2 thing, again, you get the same value, right? So all in all, there are a lot of different ways. So you did it manually, right? By manually, I meant this, the table, right? You can do it in R. You can do it on the website, right? You can do it with the normal random variable or the standard normal random variable. So lots of options. But all of them give you the same answer. So that was for question B. Again, if you're doing it for less than 18, same thing. It's directly going to be x less than 18. If it's between 19 and 21, so it's mainly x less than 21 minus x less than 19. And if it's 22, 25, it's the same as B. But basically the last question was just to tell you that you'll get a super low value. Okay. Because it's much away from the mean. Okay. All right. So that's one of the main questions. So I think we have explored everything, all possible ways of solving these questions. So it should be fine now. Okay, moving on from normal distribution, but again, we will still use normal distribution, yeah. What's wrong with this? Okay. The number of bits they're received in a digital communication channel. Assume that the number of bits received in error follows a binomial random variable, and assume that the probability that a bit is received in error is 1 into 10 to the power minus 5. If 16 into 10 power 6 bits are received, what's the probability that 150 or fewer errors have occurred? Oops. Okay. So, okay. So binomial distribution, we have to have the value of n and we have to have the value of p, right? So n here is 16 into 10 to the power 6, all right? P here is 1 into 10 to the power minus 5. Okay. Now, obviously we can solve it the binomial distribution way, but we are going to solve it the normal distribution way. And yes, so the main argument there was that NP and NP into 1 minus P should both be greater than 5, which they are in this case. Okay. So the probability that X is greater than 150. Okay. Now, again, obviously it's 1 minus X less than 150. And what was the exact thing? Yes, so it's you add 0.5, subtract NP and root. All right. So that's going to be 1 minus P Z. So that's 150 plus 0.5 minus NP, is it? Yes, NP. So N into P, that's going to be 160. Okay. And then you have to take a root of 160 into 1 minus this value. So it's actually going to be 0.00000. Oops, it's actually going to be 9999, isn't it? Sorry for the mess here, but another 9. Okay. No, wait. Okay, I think you can solve this. So what's going to happen is it looks something like this. Z less than, if you solve this up, it's going to give you a negative value, right? Because 150 minus 160 plus 0.5. And then again, this is all solvable by normal calculators, right? So now you get minus 0.75. Okay. The question is 150 or fewer errors. So we don't have to do this. Okay, let me erase it. This doesn't have to be done because it's already fewer than the question already says fewer than. Okay. So that's that. And okay. Now you're looking at a standard normal distribution. Again, any one of the values that we just talked about. Let's give it a go. Minus 0.75. So this was 0 and 1. Minus 0.75. This thing. So that's 0.22663. And that's what the answer is. Yeah. If you also solve it using P norm, right, you can also solve it using that. So you get the same thing. 0.2263. Again, you don't have to go into so many decimal places. 0.23 is enough. All right, that's that. Then just like we did for binomial, now we have a Poisson distribution with a mean of 1000. Okay, so lambda in this case is 1000, right? So probability that 950 or fewer particles are they enter the hole. So X has to be less than 950. Again, doing the same thing for Z. We'll solve it 950 plus 0.5 for the continuity correction, minus the mean and upon root of variance. So that's standard deviation. So that's root of 1000. Root of lambda. Again, solve this. So you get Z less than minus 1.5. I just have this already solved with me, just because these are calculations. But please stop me if something's not clear. Okay. Again, you have two ways of solving this. You can do a P norm, the CDF for normal distribution, and that gives you 0.58. This was minus 1.57. Minus 1.57 also gives you the same thing, 0.058. Okay. So that's the answer. Okay. Okay. Now these questions, the both questions for exponential distribution. So the first question is, suppose that a number of kilometers a car can run before its battery wears out is exponentially distributed with an average of 10,000 kilometers. So yeah, so average, which is expectation, that is 10,000. And that you remember is 1 upon lambda. If a person desires to take a trip of at least 5,000 kilometers, what is the probability that the trip is completed without replacing the battery? Okay, so this is like a normal question. I mean, you can solve this. So lambda is equal to 1 by 10,000. The question is P x greater than 5,000. So obviously we can do it 1 minus P. That's going to be x less than 5,000. Now again, this is exponential distribution, so nothing about normal distribution here. So that's that. And if you remember the formula for this thing, for the CDF, right? So that's 1 minus e to the power minus lambda x. One minus e to the power minus, this is lambda, and x is 5,000. Okay, this 1 and 1 cancel out, minus minus sign becomes plus. Now you have e to the power, this is half minus half. So the value of e is, I mean, of course you have this in calculators, but still the value of e is 2.718. So e to the power minus half, so which is 1 by e square. Oh, sorry, 1 by root e. So that is 0.607. Again, you can solve this in calculators. But yeah, so that's how you'll solve this question. Are we good until here?
Okay, ma'am. Yes, ma'am.
Yes. Okay, great. Thanks. So this was simple question exponent. The thing is, now what you were asked here, 1,000 kilometers. So this is in kilometers, this is also kilometers. Next question. In a computer network, user login to the system, which can be modeled as an exponential process, has a lambda of 25 logins per hour. So we talked about this lambda has units of 1 over x. So it's per hour. What's the probability that there are no logins in an interval of 6 minutes? Second part, what's the probability that the time until next login is between 2 and 3 minutes? So, now here we're talking about minutes, right? So either you convert lambda to minutes, like per minutes, or you asking, or in terms of the question, you convert the question into hours. Okay. So for the first question, it's greater than 6 minutes, right? So maybe what you can do is you can call it as 0.1 hour, right? Greater than 0.1 hour. For the next question, what you can do is you can convert this into 0.033 hours, right? And 3 minutes is 0.05 hours. Just dividing it by 60. Okay. The question still stays the same. You can use this value of lambda. This is going to be the value of this thing here, x, right? Again, it's going to take me a little time to solve, but I can just share the answer with you. So for first part, you get 0.82 as the answer. Okay, so just so that when you solve, you know. And for part 2, you get 0.15 as the answer. Okay. All right. So And of course, the other way you could do it is you can convert it's 25 logins per hour. You can convert it to how many logins per minute. So that's going to be 25 over 60. That is also absolutely correct to do. But just ensure that the lambda you're using and the x you are using, they are in the same unit. Because again, it's like at this point you're canceling out, but you can't cancel out minutes with hours. Okay, fine. Okay, I think the major solving questions are done. Tell me, this is something that one of you has to definitely answer me. What is the what could be one of the outcomes of the command runif 7510? Can you, maybe one of you can elaborate on what this command does, and then which one should the answer be most likely?
C, ma'am.
Sorry, say that again.
C. Option C, ma'am.
Option C. Why do you say that?
Number C 7, ma'am.
Number of that's 7. That's absolutely correct.
Okay.
However, option D also has 7 things. So maybe C and D can both be the answer. What do you think?
D, ma'am.
D. Why do you say D now?
In third option, the highest number is 16,
Yes,
and the
correct.
less than 10 is required, ma'am.
Perfect. Perfect. Absolutely. That's exactly how you have to solve this. So you have to have 7 numbers given, and all of them have to be between 5 and 10. So this has only 5 options. That can't be there. This has 4, 5, 6, 7, 8, 9, 10. This is 10 options. That can also not be there. Both of these, as you said, have 7 options, but one of them here is greater than 10. Okay, cool. Okay. If x is a normal random variable with mean 5 and variance, so this is sigma square, that's 25. And this sort of a notation, theta something, denotes the cumulative distribution function of the standard normal variate or variable. Then what are the values of these? Okay, so this is not, I mean, it's not a very difficult question, but I'll just tell you what's happening here. So again, so we have been solving this, right? So x less than 10, if we convert it to a standard normal variable, what we can do is z less than, so 10 minus 5, 10 minus 5, and then we divide it by sigma. So that's 5 again. So that's going to be pz less than, this is 1, right? And z less than 1 can be denoted as theta of 1. So again, theta of whatever number denotes the cumulative distribution function at up until that point, right? So theta 1, which looks like this value here, that's definitely what px less than 10 is. Now, px greater than minus 5, yeah, so x greater than minus 5, so 1 minus p z less than minus 5 minus 5 upon 5, right? So this is the in question here. Okay, again, I don't want to rush, but so x greater than minus 5, that's same as 1 minus p of x less than minus 5. And then rather than saying x, I'm converting it to a standard normal. So minus 5, then minus the mean divided by the variance. So that's 1 minus p z less than, that's minus 10 by 5, so that's minus 2. Now remember, we did a lot of these original things here, right? So less than minus a and greater than a and less than a is 1 minus alpha and all of those things, right? You remember we did this. So for this thing here, now imagine this is your standard normal. This is centered around 0. We are taking minus 2 here. And this is 2 here. So when you're saying 1 minus this area, like, so this is this area, you're actually looking at this entire area now. This entire area is same as saying this entire area, right? And that entire area is basically same as z less than 2. So this thing. Okay, again, this is a very forced sort of a question. It's just to sort of explain that when you have a normal distribution, because of its symmetric nature, the same thing can be denoted in two different ways. Okay. So the right half of from minus 2 and the left half from 2, they are both the same thing. Not half, but the left portion from 2 and the right portion from minus 2. Okay. All right. Fine. Then I think there's just final two questions where you have to specify some. Just tell me what sort of a command would you use. So what command in R will you use to compute the probability P x like 25 greater than x greater than 15, where x is a normally distributed variable with mean 5 and variance 16. So we have discussed 4 commands for each sort of distribution. Which of the 4 commands are we going to use? And how? Like, would it be directly that command? Would we subtract, add?
P norm,
Yes, correct.
P
And
norm, 25,
yes.
comma, mean is equals to 5,
Huh.
comma, and SD is equal to 4.
SD
Minus,
4, yes.
minus, same thing is repeated. Instead of 25,
Huh.
15 is complement.
Perfect. That's so exactly this is what you're saying, right? Yes. Cool. All right, great. And then similar question. In a large computer network, user login to the system can be modeled as an exponential distribution with mean to be 4 logins per minute. What R command is going to be used to generate 8 random variables from this. So now we're talking about exponential function. Just if you want a reminder, for the exponential function, we are using something called rate here. Right? This rate here, and the rate is lambda. So yeah, I mean, we're using lambda, but oops, yeah. So what do you think? So what's lambda here?
1/4.
Yes, very good. So this is the most important thing here. Yes. So also for this question, don't get confused by this notation. Typically, sorry. So typically we are writing it like this, right? But anything is okay. Like it's both correct. And yes, for this one, your expectation or mean is actually 4. So lambda, which is the rate here, that's 1/4. So that's 0.25. Right. So yes, so when we solve this question, you'll have the yeah, so the command is rexp, and then bracket you'll say 8 comma 0.25. Right, so it's going to look like this. Yes, this thing. All right. Okay. Um, yes. So that's pretty much what I think what I had. Um, do you have any questions? Otherwise, we have come to the end of week 7. This was, in my opinion, relatively one of the intense weeks. Lot of things, lot of sort of formulas. But yes, but definitely normal distribution is something which is used extensively. So it only makes sense to use it as much. So again, just reiterating, in for if any of you have registered for the final exam, the questions would look a lot similar to your assignments. So, but you would not have access to R, and you would also not have access to, suppose, this sort of a web application. So in that case, the only option for you to be solving these questions is using a manual calculator to get like some of the solvings, some of the things that we solved, like maybe something like this, dividing 2 by 60, or all of these sort of calculations. And once you've reached to a standard normal distribution in the form of less than, so a CDF sort of a thing, then you can go and use the table if the table is provided, or you might already be given those values. But yeah, but that's how it's going to be. So again, today or for these assignments, definitely try the different methods, but ensure that you're able to do it the manual way, because that is what you'll have to do during the exam. Okay.
Excuse me, ma'am.
Yes.
Yeah, I have a doubt.
Yes.
Okay, we have used denorm command for finding densities.
P norm. Yes. Oh, norm, the
Uh,
first one. Yes. Okay. Yes.
denorm command.
Yes.
But as we have seen, in case of continuous distributions, exact point probabilities are 0.
That's true. Yes.
Then what exactly value does that command give? If I give denorm x is equal to 2, let us say mean is 0 and standard deviation is 1.
Yes. So for example,
What kind of values it will give?
suppose, is it this one, for example?
Yes.
Yes. So basically what this is telling you, it's not probability, it is what is there on the y-axis. So basically what it's
Okay.
is fx. So
Okay.
for example, if you have given -1 here, then this value is what it's telling you.
Okay.
It's not
Okay.
probability. But yes, it's a very good question, and I'm glad you clarified that. So yes.
Okay. Okay. So,
Uh,
thank you. Thank you
yes.
so much.
So this is, like we said, this is PDF. Yeah. I think I've just copied this from previous thing, but yeah, this is not correct. Yeah. So it's fx. Yep. Alrighty. Okay. Anything else?
No, ma'am. No.
All right. Okay. Then thank you everybody for joining in. Yes, thanks. So the deadline for this week's assignment is day after tomorrow, 12th of March. And I will meet you again next week, Monday, same time, same Zoom link. I will put in the recording on YouTube and upload the slides and the R script on the Google Drive. Okay. Thank you. See you next week. Bye-bye. Good night.